Awesome. Great. So thanks so much for the organizers for organizing this wonderful workshop, and thanks for really excited to be here. And it's also awesome to be following Jacob and Faisal for their really inspiring talks. I'm going to tell you a little bit about. Make sure the slide come up okay. Yeah, I'm going to tell you a little bit about sort of like our learning and sometime battle scar over the past decade or so in trying to exploring AI for precision health, right? And so let me see if I can advance the slide. So I want to start by with sort of a observation, right? And so if we think about it, technology have historically turns out to be the most powerful democratization forces. Every one of us in the room today, right, have much better healthcare compared to any king and queens in the history, right? So therefore, it's not sort of like too kind of like ambitious to imagine that one day we would be able to democratize high quality healthcare for everyone, that to enable them, empower them to have the same kind of healthcare as people with the most resources, right? Like Bill Gates and Steve Jobs. And also, it's actually turns out this is not even the most ambitious goal we can do, right? Because Steve Jobs unfortunately still succumbed to the cancer, and today actually like we all know that the medicine is still fundamentally to a very large extent not precise. So there is a huge growth space. So can we actually be even more ambitious to say, can we actually get to a point to actually empower everyone to have even better healthcare, right, than today's Bill Gates and Steve Jobs? So we'll argue actually throughout the talk, we basically try to argue that actually both of the goal is potentially attainable. In fact, a lot of the actually the technology and the data, the confluence of them even today, right, actually make this two goal already kind of like within our line of sight. So fundamentally, what we are going to do, sort of the technical approach is essentially try to think about sort of like, I'm an NLP guy by training, so I tend to think about sort of like a lot of this information about patient, right? They are like, when you think about cancer patient, you start from non-invasive radiology, CT, MRI, then you got resection, biopsy, you got digital pathology, multiomics. Each of those modalities is trying to tell us something about patient. But we need to learn about their language so that we understand what they're trying to tell us, right? So fundamentally, our overarching technology sort of pursuit, trying to see if we can master those language and start building up this sort of essentially virtual patient, a patient kind of like digital twin. And of course, AI is no magic, right? What might sometimes appear to be magical is actually when you put the AI algorithm onto the right kind of data. And the really exciting time is that in the past couple of decades, right, obviously, as we all know, that there has been kind of rapid digitization of a lot of those relevant clinical data. And in particular, this kind of like decades-old dream of real-world evidence that is now finally become a reality. So at a nutshell, sort of like real-world evidence is essentially is like we observe that actually every day there are kind of like billions and billions of data points capturing, right, a patient's journey from diagnosis to treatment to outcome, right? And that's essentially a population scale free lunch. And the question is that whether we can figure out the recipe to actually get to eat it, right? And so now, obviously, for folks who are familiar with real-world evidence or RWE, this is not a new idea, right? People have been milking claim data for decades. And here, what's actually really exciting, sort of like this, sort of like transformational, is that there is traditionally the real evidence focusing on kind of like the readily available structured data, right? But they are very limited. And now we actually have an opportunity to start harnessing this latest GenAI to start to make sense of those vast majority of information that bury inside those unstructured data. So let me try to make our discussion concrete by showing two kind of concrete examples. The first example is about clinical trial matching. As you know, like, today, even after all this amazing progress, right? Cancer still, standard of care still doesn't work for for many patients. And then if that happened, then the last hope often is a clinical trial. But unfortunately, even in the US, right, there is only a tiny percentage of patients who actually are matched to the trial, whereas actually, ironically, on the flip side, lots of trial fail because they couldn't find enough patients in time. And then obviously, we all know that drug development is horribly slow and expensive. So this is actually one of the marquee example, as we will see later, that actually we even today with today's technology, we can already democratize this very high quality kind of healthcare, right, for every patient, literally, and also potentially drastically accelerate drug development. But also, arguably, even today's best, medicine actually often are not sufficient, right? So, for example, in cancer, it's very exciting to think about sort of like how we go from initially like chemo killing every dividing cell to now targeted therapy, to have a guided missile to target the specific mutant protein domain, to today sort of like the cutting edge of immunotherapy, right? So previous generation of treatment, unfortunately, oftentimes cancer recur after a while, right? But immune system is probably the one health system that already natively armed by natural selection, so can deal with all those variants and mutations. And indeed, you have seen some of the spectacular success for some of this kind of like various immunotherapy like checkpoint inhibitor. But even the best drug, best of the breed, like they only work for kind of minority of the patient today, right? So that's a very frustrating kind of state of the union. But actually, there is a lot of information, for example, in digital pathology that Faisal and others had done wonderful work there that actually can give you a lot of the hints about whether the patient actually can respond or not, right? So this is kind of like another marquee example to show that actually we can potentially, go beyond even today's, healthcare common sense. And then when we think about sort of like drug discovery or even medical drug development and medical discovery in general, oftentimes we've kind of like set eyes on the early discovery, and indeed this is foundational and very exciting. But in the grand scheme of things, actually it's a minority of the costs and time. And actually, a vast majority of the time and costs actually are spent in the much more mundane later stages, like when you run clinical trial, and also even after the drug get approval, that actually there is a lot of post-market study. And this actually turns out to be kind of the really fertile ground for real-world evidence to immediately have impact, as we will see in a second. Now, so all these sound very exciting, but the question is that can AI deliver, right? So we have heard sort of all this kind of major paradigm, right? So earlier this year in Davos for World Economic Forum, people joke about 2023 is a GenAI, right? 2024 is a multimodal, and 2025, the latest buzzword is agent, right? And indeed, there is a lot of exciting progress, but as we all know that there is still huge growth space. So that's kind of like really reminding me about sort of like this Amara's law, right? So we often tend to kind of like underestimate, so we tend to overestimate short-term progress, which actually lead to the hype, right? But in the same time, we often underestimate the long-term progress, even though kind of major transformation already happened. So in Gen AI in particular, actually there is already major transformation happening on the left-hand side. So what I would loosely call the productivity gain. So this is the regime where actually human experts are perfectly capable of doing, but they're just so repetitive, tedious, time-consuming, and expensive, right? And this is exactly where even today's frontier AI can already make a big difference, especially in the text modality. Now, we are still very, very far away from automating discovery, right? And for creativity gain, but every step away along the way can actually unlock a massive value creation there. So let me start by illustrating some of the low-hanging fruit on the left-hand side of the productivity gain, right? So for example, when we think about clinical trial, obviously one bottleneck is to deal with those parsing those complicated inclusion exclusion criteria. And now actually 2 years ago when GPT-4 just came out, we actually tried really the dumbest thing you can do, right? Like write a very naturally sounding instruction. And amazingly, out of the box, right? GPT-4 can already parsing those kind of like complex matching logic. But as you can, as anyone who have worked on clinical trial matching, obviously that's not the bottleneck, right? So pharma can obviously pay for people to structure all the trial. The bottleneck is actually on the patient side, right? So for example, here's the identified journey of a cancer patient. Each bar is one particular clinical notes, right? So each note contain obviously lots of details that are required to do the clinical trial matching. Now, amazingly also that this is also where the current frontier AI already totally shine. And so in the past, you probably, for each attribute, you probably develop maybe a rule-based system, expert system, or maybe train a supervised learning system. It's not too bad if you just have one attribute to extract, right? But very soon you will suffer the so-called death by a dozen cut problem, right? When you have hundreds, if not thousands of attributes you have to structure. Now, amazingly, so frontier AI can actually a single model with very naturally sounding prompt, right? Arguably the minimal, you have to specify what you want to extract, can already do a very good job, oftentimes matching or even surpassing kind of like the best supervised one. I also particularly want to highlight the fact that actually for some of the really difficult, extraction, right, structuring, like for example, clinical staging that are very complex, right? You have this 600-page book, right, specified for each cancer drug, for each cancer type, like how do you actually determine the staging and over the year actually change, right? So on December 31st, the staging may be 3B, right? 3A, and then on January 1st, actually become 2B, right? So that's the most frustrating thing for supervised machine learning. But amazingly, with frontier AI, you can actually ask them essentially to read the freaking menu by putting the instruction in the prompt, right? And then it was able to actually follow the instruction. So those are all, and here is a very concrete example, what are all this impact, right? So every year globally, there are 20 million new cancer patients and it's bound to rise. Traditionally, you hire a medical abstractor, it costs hours and hundreds of dollars to kind of structure to abstract for a single patient. Now you could do this in seconds, costing a few cents, right? So that actually drastically unlock a lot of potential kind of like value creation, not to mention like equities and access. So one of the obviously concrete example is that you can now actually do so-called just-in-time clinical trial matching, right? So you can actually have frontier AI just reading the text, reading incoming notes all the time. You can also have it reading all the protocol change all the time. And then it can basically reflect for you, any time point, right? What are the match candidates, and you can completely reimagine how do we do clinical trial. So we have some really exciting kind of like sort of end-to-end proof point with wonderful collaborators at Providence. So very encouraging. But so this is in the grand scheme of things, all these are already happening and very exciting. But in the grand scheme of things, this is just an appetizer, right? So the really kind of like challenge ongoing is that when you think about all those notes, right, even though today they are kind of like your ultimate source, 80/20 source for what happened to the patient, but they are actually imperfect human translation, right? So just ask your radiology and pathology friends, right? They can tell you sometimes they don't even agree with themselves, right? Sometimes you turn the image 90 degrees, they see different things, right? So the question is that how can we learn to actually go one step forward, right? To actually learn to interpret those kind of like information. And each of those modality actually give you something, but neither of them, none of them standalone actually give you everything. So only by synthesizing all those modality can we recapitulate sort of a holistic kind of like patient representation. Obviously, this is very exciting, but we barely scratch the surface right now, right? So When you think about the big picture, right? So no, even the best doctor in the world, right, can never kind of like internalize, 30 million paper in the PubMed or 8 billion patient journey in the, in the world, right? But GenAI can potentially empower human expert to actually get closer and closer to that goal to actually unlock the ultimate kind of like creativity gain, right? So we are pretty fortunate and excited to have wonderful, team and collaborator to make some tiny bit of baby step. But let me, before we dive into sort of like some of those progress, let me sort of like framing this problem kind of like in a sort of like a little bit nerdy machine learning way, right? So what is precision health from a machine learning people's point of view? Arguably, we can think about it as essentially just learning a function, right? That take input of all those multimodal input, right, for the patient. And you just need to predict two things. One is the prognosis, right? So how would the disease progress? What's the risk assessment and so forth, right? The other one is the counterfactual treatment response, right? If you can predict those two kind of like medical event very accurately, right? We then have a pretty good weather forecasting system for a patient, and then we will basically make a big leap forward for precision health. Now, obviously, this is obviously very, very difficult, right? So the multimodal input is not just a snapshot, but it's actually longitudinal, time series, and more frustratingly is that most of the information you care about actually would not be available, right? And even the one that are observable often have noise and all sorts of kind of problems. But this is exactly where GenAI actually can shine, right? So the GenAI, the generative, actually come from generative kind of model in probability kind of theory, right? So essentially, what we are trying to do in self-supervised learning, at least in a big part of this generative pre-training, is that we try to learn a joint distribution of all those relevant clinical variables, right? And then once we do that, we will be able to kind of compress all those kind of observable information into this, what we can loosely call a patient embedding, right? And then we can also conduct a probabilistic inference, right? Conditional probabilistic inference that conditioning on everything you have seen, right? What are those missing things that you wish you can see, right? And then all those kind of like crystal ball prediction for the future, right, is basically a special case. So this really motivated our overarching agenda is like, can we harness all those digitized, available real-world data to portray a powerful frontier biomedical model, right? And with the GenAI disruption, we now have a chance to potentially really start to imagining and tackling a high fidelity digital twin for the patient, right? And in turn, if we succeeded, even in a sort of like to a kind of like initial 80/20 extent, we'll be able to immediately run this universal kind of like patient like me reasoning, right, across the board. So this can immediately help improve patient care, right? So the first thing that a cancer patient will do, right, is like, can we ask for a second opinion, right? Now, if you have this kind of like patient digital twin, you can snap your finger, immediately get a million second opinion, right? So you can look at what happened to all those similar patients and which drug actually have been tried and what is the outcome, etc., right? But also on the flip side, you can also compare the exceptional responder versus the non-responders, right? You can start to probing those mystery, like why the checkpoint inhibitor doesn't work for this 80% of the patient, right? So in the very near term, you can improve companion diagnosis, but in the longer term, you can actually start to come up with hypotheses about mechanismally what is the resistance, and then you can start to lead to kind of discovery. So one way to that I would love to think about this is that with all those kind of like billions of patient journey, right, there is actually a lot of hidden kind of gem, right, that insight that we can distill to actually now acquire to empower those next generation frontier model with emerging properties, right? And so one of the challenge is that and we are literally asked by our CEOs and exec, right, 2 years ago, is that should we just wait for GPT-6, right, to solve all this for biomedicine, right? So one of the observation is that number one, there is actually relatively scarce those kind of multimodal longitudinal data in the public web, right? So those frontier model out of the gate, out of the box, actually have relatively kind of like a limited capability and actually a lot of huge kind of like competency gap for any non-text modalities, right? So on text is basically semi-soft, but beyond text, actually, they have a giant growth space in the in the competency gap. And also another really potentially exciting but also challenging fact is that we keep getting more and more exciting technology, right, to get those modality. But each modality at the beginning, right, or maybe even in the long run, right, actually they are still relatively scarce, right? So how we often don't have the kind of like the brain dead regime that we can just throw GPU rack to solve the problem, right? We often actually have to make do with relatively small scarce data in each of those long tail modality. So then there is actually a lot of room for innovation to figure out how can we most efficiently kind of like leveraging all the free lunch we can get, right, to most efficiently bridging the competency gap for those emerging modalities. So I will basically, unless you haven't noticed that I am a big believer for free lunch, right? So I want to highlight 3 big sources of free lunch. And first, let me start with the unimodal pre-training, right? So the self-supervised learning that everyone is familiar with. Obviously, one big kind of like unifying scheme would be you introduce this pair of encoder and decoder, right? So then you can basically suddenly turn any unannotated kind of like data point into a training instance already, right? So if you have an unannotated image, or if you have an unannotated protein sequence, right, you can basically all use this paradigm to force the model to recapitulate the input and thereby actually start to learn a very good compression, right? And for text, we don't have to do anything because we already have great models there. Now this scheme is quite general, but for any individual modality, there are still lots of challenges, right? So the scheme basically work in a high level, but then there is still a lot of idiosyncratic problem for individual modalities. So here, I will kind of like using digital pathology as example. Obviously, you just heard a wonderful talk by Faisal, right? And so here I basically will kind of go from a very particular angle, right? So that is a very focused angle about tumor microenvironment, right? So it's widely believed that why those immunotherapy doesn't work, the secret lies in the tumor microenvironment. In particular, you can basically look at the digital pathology slide and others, right? You can start to interrogate like, hey, where are the tumor cell? Where are the stroma cell? Where are the immune cells, right? And how they basically situate next to each other essentially actually bury a lot of secret insight, right? To tell whether the tumor is hot versus cold, right? And whether it will respond to immunotherapy or not. And if a tumor is cold, right, which means that actually oftentimes the immune system have no idea where is the tumor, right? In that case, if you run the immunotherapy blindly, then the immune system don't know where to go, right? It mobilizes an army and then just will attack the normal cell, and that's what lead to sort of like autoimmune overdrive that sometimes kill the patient before the cancer. So ultimately, what we would love to think about is that can we learn to master this so-called tumor microenvironment grammar, right? Because essentially, that's just like how those cells actually place next to each other, right? That spatial configuration, that's really lies a lot of the secrets. So that's kind of like really sort of the long-term agenda that we're trying to do this. Now, this basically forces us to start to confront some of the really fundamental challenges with digital pathology is that, for some simpler tasks, right? Like let's say, subtyping or some of the pretty kind of like obvious features, then we can get away with just looking at relatively local patches. But if we actually really want to sort of induce a global view about the human microenvironment, we have to actually model the entire slide all at once, right? Now, theoretically, we have the perfect tool, like transformer, right? So basically for images, how it works is that you basically have every pixel exchange messages to every other pixel, right? So that's basically what all those layers unrolling, right? The message passing for multiple runs. So, and after you are done, you can actually essentially capture arbitrary complex patterns. So that's what the transformer is powerful, but then that also lead to is kind of potential downfall, right? So by having to do this pairwise message passing, that means the computation scale, quadratically in terms of the pixel, right? So unfortunately, digital pathology, as Faisal and others have mentioned, right, is some of the largest images in the world, right? So a single slide, right, can cost you a computation if you do it naively, potentially billions of time of standard web images. So there are many potential ways to tackle this problem. And one of the particular approach we mentioned actually even last year is that this idea that we basically steal from speech recognition, who also have to deal with this long context, right? So the idea is actually really, really simple, right? So if we already did a lot of message passing locally, right? So that means like everybody in the neighborhood already pretty much know every of your neighbors, right? So that means like when we actually try to pass messages from the local patch to some patch far away, right? Instead of having every single person to exchange message to every single person in the other patch, right? We can potentially elect a representative, right, for the local neighborhood, and then and just focusing exchanging message in that way, right? So that's essentially the sense of what we are doing this, right? And we are very excited to have wonderful collaborators with Providence and University of Washington to actually come up with this sort of first attempt to really try to scale transformer to the gigapixel whole slide. Some of the things that I wouldn't bore you with some of the conventional kind of like evaluation, but one thing that actually caught our pathologist's eyes is that we try to force the model to learn this pan-cancer signature across 31 cancer types, right? So initially it sounds crazy because every single cancer have different morphologies, right? So, but I mean, in the age of GenAI, you have to try, right? And then surprisingly, for some of those biomarker, it actually does find some pretty strong signal. Now, of course, that could come potentially from some other confoundings and so forth, so we still have to follow up. But that's actually something that actually is surprising to our collaborating pathologists, and so that's kind of like really kind of interesting. So since last year, we are very excited to see actually over 1 million downloads globally, and so we're looking forward to hear more from the community. And so far we talk about unimodal pre-training, right? But there are even bigger challenge that lies ahead, right? And the problem here is that each of those modality trying to tell you something, but each of them is speaking in a distinct language, right? So for example, CT may be mapping the tumor lesion somewhere in the embedding space. Digital pathology may be mapping the same lesion in somewhere else. So each of them basically like, maybe CT is like Hindu, digital pathology is French, right? So how can we get them talk to each other, right? So again, I'm an NLP guy, so we look at kind of playbook in the machine translation. Turns out that's exactly the problem they have to deal with, right? So, and one common principle they do, right, is by grounding every language into one really resource-rich language like English, right? So let's say you take a look at, maybe a sub-language in India versus some language in African, there may be zero parallel data between them. But what you could do is to using English as a pivot and a bridge, you can translate from an African language to English and then translate back to some sub-language in India. So that's literally how machine translation scale to hundreds of languages in the world. And what we are proposing here is to using the text modality as that interlingua, right? So there is lots of reason to do that. One of the obviously a major reason is that we already have the powerful LM. And another reason is that for anything we do in biomedicine, we often conduct it in natural language, right? So that means like every modality you study, you often leave a lot of paper trail, right? So that means that there is a lot of naturally occurring modality text pairs. Now here's what we are trying to do is that it's a little bit different than the contrastive learning, right? So which is what wonderfully well for two modality. But once you get to, because you basically try to induce a common embedding, right? You learn as you go in contrastive learning, right? Now that worked perfectly well with two modality. Once you got 3, 4, 5, you start to get a 3-body, 4-body, 5-body problem, right? So here basically we are trying to take a different kind of trade-off, right? Try to say, let's ground everything into the text modality. Now we can piggyback on what we have done in the unit model pre-training, the encoder and decoder of your favorite, but we're just focusing our computation by leveraging those modality text pair on focusing on learning a very lightweight adapter layer, essentially the translator, right? I wouldn't bore you with some of the technical detail, but you can check out the LaraMed, which outline one kind of like general principle, right? And using kind of like this kind of approach, one really exciting progress is that we were able to kind of like using text as a unifier, right? Enable people to conduct holistic image analysis essentially using natural language, right? So you can basically talk to the image, right? And then to identify the objects, to segment the objects and so forth. So this basically is our biomed parser work, right? So actually Theo is in the room. You should ask him more about this. This basically captured 9 imaging modalities and 64 object types. We are very excited that Nature Method also published an independent review that say some very encouraging things about this. We are also very, very excited about the organizer actually organizing a text-guided image segmentation, and really excited to look at the progress along this direction. Now, so far we talked about 2 free lunch. Let me quickly talk about the final and probably the most important one, right? So, which is that actually even those radiology report, pathology report, they are not actually perfect translation about the images or anything, right? So those are just a human interpretation. But if you look at the longitudinal journey about the patient, you do actually get unambiguous output, right? Like let's say 6 months later, 1 year later, does the cancer recur? Does the patient die, right? Those give you basically unambiguous kind of like information that you can go feedback to really update your embedding models, right? So basically, we essentially propose that we can just focusing on just like GPT-4 learn by predicting next token, next token, next token, right? We can just view a patient journey as medical event, medical event, medical event sequence, right? And in this way, we can basically conduct a self-supervised supervision by predicting the next medical event. We did some very, very tiny baby step to establish the scaling law. On some of the public data set, we are now trying to scale to really population level. So hopefully in a couple of months, we will have some really exciting work to announce as well. So to conclude, I would say that obviously to echo some of the earlier speakers, right, that there are very exciting work that to be done in the pre-training, in the self-supervision, in particular all the other modality, right? So CT, MRI, single cell spatials, and so forth. Very exciting to see the chronos and other work, right? There are also really exciting growth space in how do you learn about the correlation between those modalities, right? And finally, like how can we scale this kind of like EHR pre-training to the truly population scale? Now, very quickly, I would mention, 3 actually really interesting directions that on the application side, one is a reasoning agent, right? And finally, can we imagine virtual population, right? For the reasoning, in the interest of time, I would just point you to the paper, but this is a tiny baby step, right? But basically it shows that when you do actually, you frozen the image model, right? So we take any VLM, we frozen the image model, but we try to actually enrich the language model with general domain text-only reasoning. Now, somewhat surprisingly, this actually helped multimodal reasoning actually in the biomedical domain, right? Which help actually the downstream tasks. So, and now retrospectively, this may not come as that much a surprise, right? Because if you saw the origin of the GPT, right? Actually, they first put training on the GitHub, codes, right? And that actually helped immensely to the language model for natural language. So there is actually a lot of commonality there. Jacob and Faisal already mentioned the tumor board. So this also have been basically essentially inspire us a lot of our early journey in precision health. So we are very excited to see some of the kind of like end-to-end kind of real world proof point that even with fairly primitive AI, I have to emphasize, right? That actually tell you how low the bar is. But then we can also start to imagine what this next generation tumor board looks like. And one of the recent exciting development is that our CEO just last month, right, announcing this agent orchestrator. It's actually available in Azure Foundry. So again, just tiny baby step, and look forward to hear how the community actually been using it. I would conclude with this sort of like somewhat provocative example, right? So with all this real world data, right, with the capability of doing clinical trial matching, what we actually can unlock is the following. Like given any clinical research hypothesis, you can snap a finger, you can now conjure up a virtual case sum and virtual control arm, right? So in fact, we show that actually for some of the marquee lung cancer, trial, we can using the Providence real world data to actually simulate to attain similar hazard ratio, right, compared to the published results, including this original Keytruda trial, one of the most successful CPI. So the question is that how far can we go, right, by harnessing the real world data to accelerate medical discovery? So I want to acknowledge my wonderful team, right? These days I'm just doing PowerPoint programming. I also want to thank all our collaborators, right, who really, without whom we obviously can't do any of this work. Thank you very much.